Today we're going to be taking a look at supercell thunderstorms and how they work. Now these storms are extremely complex, so I'm going to do my best to give you a simple yet thorough explanation of how they work. Like all thunderstorms, supercells are the result of atmospheric convection. Convection in the atmosphere is the result of instability, which we measure using something called CAPE, or convective available potential energy. This is essentially a measure of how much energy in joules per kilogram will be released if a parcel of air rises through the troposphere. The larger the value of CAPE, the more energy there is available for storms. The second important ingredient for supercells is something called wind shear. It is essentially the change in direction and speed between winds at different altitudes. The greater the difference in speed and direction between altitudes, the greater the shear. The wind shear causes an updraft rising through it to rotate, typically in a counterclockwise direction in the northern hemisphere. If this rotating updraft is persistent, we call it a mesocyclone. Here I've overlaid an actual thunderstorm over this QT plot on a day when tornadoes occurred nearby to give you a better idea of what the instability and wind shear look like as we ascend up through the troposphere. There is an important layer of the lower atmosphere that is visible where the lines of the plot intersect right above the surface, and we call this the cap, and is extremely important to building instability and is something I will go into much more detail on in a future video. So this is what you might see driving on a day when the conditions for supercells are favorable. Clear skies with towering cumulus in the background as convection starts to get underway and the cap breaks. These towering cumulus will go on to become intense thunderstorms and as we draw closer, we gain visual on a cell directly ahead of us. Although we are still quite a distance from this storm, visual clues in the form of storm structure are present that tell us that it is likely a developing supercell. If we look closely, we can see a flat section of the thunderstorm that contains absolutely no rain. This is the storm's rain-free base or updraft base, and it is where the storm is drawing in warm air. This air then rises up the updraft tower at an angle and descends downwind as the storm's downdraft. These are signs that our storm is being shaped by wind shear in the atmosphere. As we look up, we can see a rapidly expanding anvil cloud as our storm's updraft crashes into the tropopause and has nowhere to go but horizontally. We look out ahead and we can see more and more precipitation falling as our storm's downdraft strengthens. We catch up with our storm and position ourselves near an overpass looking west with a clear view of our storm, which has matured into a classic supercell. The first thing that stands out to us is a large barrel-shaped rotating updraft rotating in a counterclockwise direction and ascending through the atmosphere at an angle. This is the storm's mesocyclone and is what drives the rest of the storm. The next identifiable feature is the large section of heavy rainfall on the right side of the image and extending off to the northeast. This is the storm's forward flank downdraft. This mass of cool air and precipitation descends from the storm and spreads out in all directions once hitting the ground. The forward flank downdraft often consists of heavy rain, hail, and damaging straight-line winds. If we look to the southern side of the storm underneath the mesocyclone, we can see a horseshoe-shaped section of clouds where no rain is falling. This is the storm's updraft base and is where the storm is drawing in warm inflow. This is also the most dangerous part of the storm to be in. The horseshoe-shaped cloud is being caused by something called the rear flank downdraft, cutting into the mesocyclone's updraft base and forming what's called the RFD clear slot. The RFD is a downdraft of dry air that is pulled down from the mid-levels of the atmosphere by the mesocyclone and wraps around the back of the mesocyclone. The RFD can contain large hail, heavy rain, and strong winds. Looking closely to the southwest of the storm, we can see a line of towering cumulus being pulled northeast into the mesocyclone. This is called flanking line convection. The mesocyclone pulls in these smaller updrafts and absorbs them, adding to its own strength. The forward flank downdraft, rear flank downdraft, and mesocyclone form a wind field surrounding the supercell that typically looks something like this, with the gust fronts from the rear flank downdraft and forward flank downdraft forming a narrow corridor of space for the storm to pull moist, warm air into the mesocyclone. This is called inflow, and as the space between these two gust fronts gets smaller, the inflow speeds up to compensate for the narrowing channel it has to travel through, dropping in pressure along the way. At the intersection of these points, the inflow can become particularly intense as it gets occluded, and although this supercell did not produce one, this is the part of the storm most likely to produce a tornado. These same features can also be identified from a radar reflectivity scan. The large lobe of heavy precipitation and hail extending off to the northeast is the forward flank downdraft. The part of the storm that is hooking back around into a ball shape on the southwest side of the storm is the rear flank downdraft, and we call this specific radar signature a hook echo. The area of low to zero reflectivity directly adjacent to the hook echo is the storm's updraft base. The area of light precipitation leading northeast towards the updraft base is the flanking line convection we saw earlier. I've overlaid the wind field again to give you a better idea of their approximate location. Once again, the area between these gust fronts is where the storm is drawing in warm inflow towards the mesocyclone, speeding up as it gets occluded. The area where these intersect and the top edge of that horseshoe-shaped updraft base is the most likely place for a tornado to be in the storm. Here I've overlaid my position and the approximate location and size of each of these features on a satellite map of the area they occurred over at the time that picture was taken. We are the blue dot sitting in the upper right corner looking west. We are sitting approximately 3.5 miles from the mesocyclone, and once again, if the storm produces a tornado, it is most likely going to be on the north side or upper side of that horseshoe-shaped updraft base. Here I've superimposed the reflectivity scan to show you where these features fit into it. Anywhere along the gust fronts of the forward flank downdraft and rear flank downdraft, incredible shelf clouds may form as warm air is forced up and over the cool downdrafts. These storms can also contain intense and frequent lightning, heavy rain and hail, damaging straight-line winds,
it's getting stronger,
and possibly even tornadoes.